Alright, okay, so today we're going to talk about section 7.2. We're going to talk about some sum and difference identities. Okay. So just as some motivation, let me give you what we have already on the unit circle. Okay. We know that this is the point 0, 1, and this is the point, 1, 0, and this is the point 0, 1. We have a few angles in here that we know, positive square roots of 2 over 2. Okay. That gives us the 45. We also have square roots of 3 over 2, 1/2 for the 30 degrees, and 1/2 square roots of 3 over 2 for the 60 degrees. And then these can just be translated to every quadrant. So these are the angles that are known on the unit circle. Now there's tons of them in between here. There's an infinite amount, but we don't know the exact angles of those. So with the sum and difference identities, it stands to reason that if we know certain angles for, say, 30 degrees, 45 degrees, this is 60 degrees, etc., well, I should be able to find the sum of these two. Say, I should be able to find what 75 degrees is. If I took 30 degrees and 45, and those are known, I should be able to find what 75 degrees is. Okay. Or I could subtract 45 and 15, and I should be able to find those. Okay. Now let's start with one we know. If I take 30 and 60 degrees, that would certainly, if I add 30 degrees and 60 degrees, I should certainly get to 90 degrees. Okay. So let's do that. So we know that the cosine of 30 degrees plus 60 degrees, okay, inside the argument, that is the cosine of 90 degrees. And that is equal to just 0. We know this, okay, from the unit circle. The cosine of 90 degrees is 0. Okay. Now, what you may have been thinking when I was talking about adding these is you may have thought, well, then that's the cosine of 30 degrees plus the cosine of 60 degrees. Okay, so let's look and see what happens there. Well, the cosine of 30 degrees is square roots of 3 over 2, then plus from the formula, and then the cosine of 90 degrees is 1/2, or I'm sorry, 60 degrees is 1/2. So when you put this together, this is the square root of 3 plus 1 over 2, and this does not equal 0. Okay. So our initial hunch, saying that I could just add the cosines of two angles and get the cosine of their sum, is incorrect. Okay? So in fact, here's what we have. Okay? Now these will need to go on your flashcards. Okay? All right, we have that there's the cosine of two angles. Let's call them alpha and beta. Okay? So if I'm going to add two angles in cosine, how I'm going to find that is I'll take the cosine of the first, alpha, and then it's always the cosine of the second, beta. Now I'm dealing with the cosine, so I will not take the same sign, so it's subtraction. And then we'll take the cofunction. So the cofunction of cosine is sine of alpha and sine of beta. Sine of beta. Okay. All right, so this is the first. Okay. Now if I want to find the difference in cosine of two angles, okay, then again the process stays the same. I take the cosine of the first, which is the cosine of alpha, and then always the cosine of the second, which is cosine of beta. Now because I'm dealing with the cosine, they'll become positive here, and then I still take the cofunctions, sine of alpha, sine of beta. Now, let's deal with sine. Okay. So if I want to take the sine of two angles, what I would have to do is the process is the same. Here I'll take the sine of the first one, which is alpha, and then it is always cosine of beta. Okay. Now I'm dealing with sine, so I'll take the same sign. So this will be a plus. And then we still take the cofunctions. So cosine alpha, sine beta. We could also take the difference in sign. Again, the process will stay the same. It's the sine of the first, which is sine of alpha, then always cosine of beta. Sine, yes, so I'll take the same SIGN, which is a negative, and then the cofunctions, so cosine alpha, sine beta. So these are the sum and difference formulas for sine and cosine. And if you have these memorized by the end of this homework, that would be great. It'll be very helpful when we do the next lecture. Okay, so I just told you what these were. I didn't actually tell you how we came up with it. So I would like to do the proof of this with you. Right? And to do that, I'm going to need to turn my page. Right? So we're just going to do one. Okay, go up a little bit. See that a little bit better. Okay, let us do the proof of the cosine of alpha minus beta. Okay. Now, as I said earlier, that's going to be the cosine of the first, always the cosine of the second. Okay. It's cosine, so I'll take the opposite sign, which is a plus, and then I'll take the cofunctions, so the sine of alpha, sine of beta. Okay, so this is what we're going to prove. Right? To do that, we're going to need to do some setup. Okay. Let's put two unit circles down. Okay, so we know that we could draw at an angle like so. Okay. It would be measured in standard position, okay, from here to here. And let us call this alpha minus beta. So that's the angle we're trying to work with here. Now, there would be some point here. This is the point 1, 0. And I don't know what this point is. And we're going to label it as x3, y3. You'll see why in a moment. Okay, this is really, we could call this x4, y4 if we wanted to. We just happen to know what these coordinates are. Okay. Now, let me shift this around. Okay, there is a distance between here. This distance I'm putting in red, it's a little hard to see. Okay, so this one's red. Now I could shift this around to say, like here, these points. So it would look something like so. Okay? These are not necessarily symmetric. Okay? By shifting these around, okay, I've kept this distance the same. And why I've done that then is that the way I've shifted it is this entire angle measured in standard position, this entire 1. That could be our angle alpha. And so this angle alpha would have coordinates, again, we don't know what they are. They're x1, y1. And then we would also have, the way we were shifting it, we would shift it so this angle was beta, and it would have some points x2, y2. So the key is, here's alpha minus beta, there is some distance here. I shift and rotate it around, keeping this distance equal. Okay, so this red distance must be equal. Okay, that's going to allow us to set up an equation here in a minute. And then what is helpful about that is then still this middle angle in between here and here stays as alpha minus beta. Okay. So if all the way around is alpha and from here to here is beta, then the difference between those two angles must be alpha minus beta, and the distance must be the same as here. So let's think about what we know then. Okay. Well, if this distance must be equal, I can use the distance formula. Okay. That is, if I take the distance between these 2 points, it'll be the difference squared plus the difference of the y's squared. Okay. I'm going to color code this. So x1, this would be x1, this would be y1, and this one would be x2, y2. Okay? It's just the distance formula. Okay? Now if I make the distance over here, okay, let's put our x3s first. Okay, so this would be x. Let me do it in orange. This is x3, and this is y3. Okay. Now the x coordinate here we already know. We don't have to label it as x4. We know the x4 coordinate is 1, and the y4 coordinate is 0. Okay. So that's just basic algebra, the distance formula, and then from the proof we know that these have to be equal from the way we've set it up. Okay, so now let's start simplifying this equation. Okay. Well, the first thing I want to do is get rid of these radicals, so let's square both sides. Okay. Now when we do that, the radicals will disappear, and we'll simply have x2 minus x1 squared plus y2 minus y1 squared is equal to x3 minus 1 squared plus y3 minus 0 squared. Okay? This must be true. Okay, now let's start simplifying. Okay. So in this case, we're going to actually have to expand before we can simplify. So this becomes x2 squared minus x1 y1, or I'm sorry, x1 x2 minus another x1 x2, and then plus x1 squared. If it makes it more helpful, you can put these in parentheses. Okay. Right. And let's just simplify that while we're at it. X sub 2 squared minus x, let's see, this would be minus 2. These are like terms. Okay. 2x1 x2 plus x1 squared. Okay. So I've just expanded this and simplified. Alright, now let's add. Because from here we're adding. Let's expand this one. Okay, so if we expand that, we get y sub 2 squared minus y1 y2 minus another y1 y2 plus y sub 1 squared. Which if we simplify, we can simplify to y sub 2 squared minus 2 y sub 1 y sub 2, okay, because these are like terms, okay, plus y sub 1 squared. Okay, now we need to have an equal sign. Okay, and now I'm going to work with the right-hand side. Okay, so here, this needs to be equal to, well, let's expand this. Okay, this is going to be x sub 3 squared minus x of 3 minus another x of 3, so minus 2x of 3's plus 1. And then plus from our formula from here. And then we'll expand this one. Well, y sub 3 minus 0 is just y sub 3. So we get y sub 3. I'm sorry, sub 3, that quantity squared. Okay. So this is our equation. Okay. Let me try and write it just a little bit more in line. Okay. Smaller so we can see this happen. So x sub 2 squared minus 2x1 x2 plus x sub 1 squared plus plus y sub 2 squared minus 2 y sub 1 y sub 2 plus y sub 1 squared is equal to x sub 3 squared minus 2x3 plus 1 plus y sub 3 squared. Okay. So this is just going to take some good bookkeeping skills here. Okay. Just rewritten this equation as in 1. So now, if we're using algebra, there's nothing else we can do here. These are all different variables. They have different subscripts. And there's no combining. There's no longer any combining that I can use via algebra. Okay. So let's go back to our diagram here. And let's rethink about what this is. Well, remember, this is a unit circle. Okay. And so really, this is the sine and the cosine, or I'm sorry, the cosine and the sine of 0. And so this is really the cosine of our angle, which is alpha minus beta, that is x3, comma, and y3 must be the sine of alpha minus beta, because we're on a unit circle. Alright, well that's fine. So if we use that logic, then x2 is associated with this angle beta, so this must be the cosine of beta, that is x2, and y2 must be the sine of beta. Then similarly here, x1 is associated with the angle alpha, so this must be the cosine of alpha, and then the sine of beta. Okay. And now one other thing that we need to keep in mind, because we're on the unit circle, remember the equation of any unit circle is x squared plus y squared is equal to 1, okay, which directly leads us to the cosine of any angle. So cosine squared, we'll call it theta, plus sine squared of theta must be equal to 1. Okay? This is our Pythagorean identity. Okay. Now, keeping that in mind, that x1s are cosines alpha. Which one? This one is alpha, not beta. Cosine alpha, sine alpha. This is cos beta, sine beta, and this is the cos of the difference and the sine of the difference. Alright, now let's apply that. So what this means then is if we had an x1 squared plus a y1 squared, we could simply equal 1. And that's what we have. Okay. Here's an x1 squared, and here's a y, or an x2, I'm sorry, I need y1. Where's y1? Here we go. x1 squared plus y1 squared. Well, these two become, let's see here, x1 squared, I'm going to rewrite this as cosine squared alpha plus sine squared of alpha. Okay. Now, plus, let's see if we can find some others. Okay. If we had an x2 squared with a y2 squared, which we have here, x2's were associated with beta. That's the cosine squared of beta plus the sine squared of beta. And now, these aren't like terms, so we'll just have to bring it down. Minus 2x1, x2, and minus 2y1, y2. Okay. Now on the right-hand side, we also have an x3 and a y3 squared, and this was associated with the cosine squared of alpha minus beta plus the sine squared of alpha minus beta. And then we'll just bring these down. Minus 2x3 plus 1. Okay. All right. And now we're just steps away from finishing this. Okay. Let's remember then that cosine squared plus sine squared of the same angle is simply 1. Okay. Then plus, and here we have cosine squared sine squared of beta. That has to be equal to 1. Okay. And then we'll just copy these. Minus 2x1, x2, minus 2y1, y2 is equal to. Now here we have cosine squared sine squared of alpha minus beta, so that's the same angle, so that's 1. And then we can subtract minus 2x3 plus 1. Okay. Alright, let's keep simplifying. Now, notice here we have 1 plus 1, well that's simply 2, then minus 2x1, x2, minus 2y1, y2. Okay. We also have 2 over here. We have 1 plus 1 is 2, so this becomes 2 minus 2x3. Okay. Now we'll just go back to some algebra. Okay, we're still trying to simplify this equation. Let's subtract 2 from both sides. So subtracting 2 just will leave us then with the minus 2x1, x2, minus 2y1, y2, and that goes to 0, minus 2x3. Now, we have these negative 2's to deal with. Let's just divide everything by negative 2. Then those will cancel. And now we have x1, x2, now plus, because the negative and negative become positive, y1, y2 is equal to x3. And believe it or not, we're done, because if we go back and remember what we were doing, x3 represented the cosine of alpha minus beta, and that is equal to, now our x1s dealt with the cosine of alpha. Okay, so x1 was the cosine of alpha. X2 was the cosine of beta. Then the plus from the formula. And the y1 is the sine of alpha. And the y2 is the cosine, is the sine of beta. And that's it. We've proved this. Ta-da! Now we're not going to do this for all of them, but notice how it was it's actually quite an easy proof. The hardest part is getting an equation that we can manipulate. Okay. So if you understand the setup, then that is why these formulas stand into reason. Okay. So we can't just do things like we did in the beginning where we thought, well, maybe I'll just be able to add the two or subtract the two that I know, when in fact that's just not true. Okay. And this is the proof why it's not true. Okay, so how is this going to be helpful to us? All right, well, let's look at some examples then, how we would use these. So, for example, I guess I can turn it back now. If we had the cosine of 75 degrees, okay, well, 75 degrees is not on our unit circle, but I could rewrite the cosine of 75 degrees as the cosine of 30 degrees plus 45 degrees. Remember your degree symbols. And why is that helpful to us? Well, now that I've done that, 30 degrees is known. We'll call that alpha. 45 is also known. We'll call that beta. Okay. So now expanding using the sum formula. Okay. Remember that the cosine of alpha plus beta is the cosine of the first, always the cosine of the second. We're in the cosine, so we'll take the opposite SIGN, and then the cofunctions, sine of alpha, the sine of beta. Okay. Now all we have to do is substitute in. So the cosine of alpha in this case is 30 degrees. Then we'll take the cosine of 45 degrees, which is beta, and then subtract off the sine of alpha, which is 30, and the sine of beta, which is 45. So now these are known to us, and so we can find them. Well, the cosine of 30 degrees is square roots of 3 over 2, and the cosine of 45 degrees is root 2 over 2. Then we'll subtract from the formula. The sine of 30 degrees is 1/2, and the sine of 45 degrees is also root 2 over 2. And now we can simplify this term by term. Okay, I'm multiplying fractions, so this becomes over 4. And up top, when you multiply radicals, you can multiply underneath the radical, and then minus square roots of 2 over 4. Okay. Now they both have the same denominator, so we can write it as one great big fraction. And this is the square root of 3 times 2 is 6, minus the square root of 2. And this is your exact answer. All right, let's try another one. Example. Let's find the sine of 105 degrees. Okay. Again, this is not on the unit circle. I mean, it's on there, but it's not one of our known angles. So I'm going to rewrite that in terms of two angles that I do know. So 60 degrees plus 45 degrees. Okay. And now I'll apply the sine formula. Remember, the sine of alpha plus beta is equal to the sine of the first, which is the sine of alpha, always the cosine of beta. I'm in the sine, so I'll take the same SIGN, and then the cofunction. So this is the cofunction cosine of alpha and the sine of beta. Okay. So 60 will be alpha and 45 will be beta. And now we can fill this in. That's the sine of 60 degrees times the cosine of 45 degrees plus the cosine of alpha, which is 60 degrees. Alpha. And times the sine of beta, which is 45 degrees. Okay. Now our setup is done. And now we can just evaluate. Well, the sine of 60 degrees is square roots of 3 over 2. I need to multiply that by the cosine of 45, which is root 2 over 2. Then here I have a plus. Then the cosine of 60 degrees is 1/2. And the sine of 45 degrees is root 2 over 2. Okay. And then by the same logic, we'll multiply these together. Root 3 times root 2 is root 6 over 4, plus root 2 over 4, which we could write as root 6 plus root 2 over 4. Okay. Now here's another one. We have to be able to do this not only in degrees, but also in radians. So, for example, let's find the cosine of 5 pi over 12. Okay. Again, this is not a known angle on the unit circle, so our job will be to try and find two angles that will add or subtract up to this. Well, I know that if I took the cosine of 8 pi over 12 and I subtracted 3 pi over 12, okay, well, 8 pi minus 3 pi would be 5 pi over 12. So we know this is true. Okay. And now we have the cosine of, now reducing this, let's see, 4 goes into 8 2 times, and 4 goes into 12 3 times. So this reduces to 2 pi over 3, which is an angle that we know on the unit circle. And here 3 goes into 3 1 time, so we'll be left with just pi, and 3 goes into 12 4 times. Okay. So this is going to be our alpha, and this will be our beta. Okay. So the cosine of alpha minus beta is the cosine of the first, always the cosine of the second. I'm in the cosine, so I take the opposite SIGN, and then the cofunctions, SIN, alpha, and the sine of beta. So here we go. The cosine, let's see, so the cosine of alpha is 2 pi over 3. Cosine of beta is pi over 4, plus the sine of alpha, which is 2 pi over 3, the sine of beta, which is pi over 4. Okay, now the cosine of 2 pi over 3, so this is pi over 3, this is 2 pi over 3. So I'm at negative 1/2 positive square roots of 3 over 2. So the cosine of 2 pi over 3 is negative 1/2. The cosine of pi over 4 is root 2 over 2, plus the sine of 2 pi over 3, which is square roots of 3 over 2, and the sine of pi over 4, which is root 2 over 2. So if we simplify this, this becomes negative root 2 over 4. This will also be over 4, plus square roots of 6, which we could commute these and write it as root 6 minus root 2 over 4. Okay. Now let's look at this example. Okay. So what if I gave you the sine of 34 degrees times the cosine of 13 degrees plus the cosine of negative 34 degrees times the sine of negative 13 degrees. And I wanted you to find the value of this. Find the exact value, no doubt. Okay, so what we're going to do here, this is testing pattern recognition. Okay, notice I have sines and cosines. Okay. And I also have the same two angles. Well, almost. So let's see if we can try and make this look like one of our four setups. Okay. Now, given that I have sines and cosines in the same terms, I'm going to have to determine if it's sine of alpha plus beta or alpha minus beta. And the only difference between those is going to come down to the plus or minus. Okay. But remember, we're going to have the same alpha and the same beta. Okay. So I almost have the same alpha and the same beta, almost. Okay. So let's think about this. Well, what do we know about the cosine of 34 degrees? Well, we know that since cosine is even, that is equal to the cosine of a positive 34 degrees. We know this to be true. Degrees, and then we have the plus. Okay, so we're almost there. Now, what about, can we make this negative 13 into a positive 13? Well, sure we can, because sine is sine is odd, so the sine of the negative angle is the negative sine of the positive angle. Okay. And now we have the same angles. Okay. But what we're going to have to be careful about here is now that we've thrown this negative into the mix, we're adding a positive and multiplying by the negative, so these two will change to a negative. Okay. So this is the sine of 34 degrees times the cosine of 13 degrees minus the cosine of 34 degrees times the sine of 13 degrees. And now we can reference our list again. So here I have a sine and a cosine of alpha and beta with the minus, and then the cosine of alpha and beta. So that means this is of the form sine of alpha minus beta. So this is equal to the sine, but in this case, alpha is 34 degrees, okay, and then beta is 13 degrees. So this really represents, now we can simplify inside of here, the sine of 21 degrees. So we have simplified it. Now, if this was a known value, we could actually find the value. So like if this was a known angle, like if this had come out to be 45, then we know the sine of 45 degrees is root 2 over 2, and we would write it. It turns out when we simplified this one, though, it was another angle that was not on the unit circle. Okay. So that's how you're going to use these cosines of alpha plus beta and the sine of alpha plus or minus beta. Some are different formulas. Okay. Now, tangent is also one of our big angles, so we need to also find that. So let's find the tangent of alpha plus beta. Now remember that that's going to be the sine of alpha plus beta over the cosine of alpha plus beta. Okay. Well, I can expand that. I know the sine of alpha plus beta is the sine of the first, always the cosine of the second, sine, so I'll take the same sine, and then the cofunctions, cosine of alpha, sine of beta. Okay. Just expanding this. Now we need to expand the cosine of alpha plus beta. So that will be the cosine of the first, always the cosine of the second, and then the cosine, so I need the opposite sign, and then the cofunctions. Well, now what? I would really like to think that we could rewrite the tangent formula, not in terms of sines and cosines, but in something much more simplistic, using tangents as well. So let's try this. I'm going to rewrite this. The sine of alpha, cosine of beta, plus the cosine of alpha over the sine of beta. So what if I divided these now? Well, if I divide this by the cosine of alpha, okay, and then let's just multiply by the cosine of beta here, okay, then I would get a tangent of alpha, because sine of alpha over cosine of alpha is tangent, and cosine beta over cosine beta is just 1. But if I'm going to do that, I have to do it for everything, so that this one would also have to be divided by the cosine of beta. And I can't just do that to the numerator. I also have to do that for the denominator. So rewriting the denominator as it stands now, and then I would have to divide these also by cosine alpha, cosine beta, over cosine alpha, cosine beta. Okay, so now let's do some simplifying where we can. Okay? We saw that the cosine of alpha, let's see, here the cosine of beta over the cosine of beta, these are common factors, so these will just go to 1. Okay? Beta, beta, this is cosine alpha, that also goes to 1. Cosine alpha goes to 1. Cosine beta goes to 1. Okay. And here, no simplifying. So let me just rewrite these. So up top we have the sine of alpha over the cosine of alpha times 1, which is just sine alpha over cos alpha. Then plus, here 1 times, we just have the sine of beta over the cosine of beta. Down below, we just get 1 times 1, which is 1, and then minus from here. And we could rewrite this as sine alpha over cosine alpha times sine beta over cosine beta, because if we were to multiply these back together, we would get this one. And now we've accomplished our mission. This is just tangent of alpha. Plus, this is equal to, plus, and this one over here, well, this is just tangent of beta. Now we're going to divide this by 1 minus, and what do we have here? Again, we have the tangent of alpha, and that's being multiplied by the tangent of beta. So in this way, we have simplified it, and we know then that the tangent of alpha plus beta is equal to this. Tan alpha plus tan beta over 1 minus their product. Okay? And we won't go through it, but in the same manner, we could find tangent of alpha minus beta. And what we would then see is that, again, we'll have this tan alpha, the tan beta, divided by 1 and their product. The difference here is that now we will switch the signs. So up top you'll have the minus, and down below you'll have the plus. Alright, so these are 6 formulas that you're going to need. Okay. The sum and difference for the sine, cosine, and tangent. Let's do an example of these then. Okay. Alright, so for example, if we had to find the tangent of 195 degrees, okay, not a known angle on the unit circle. Right? So we're going to rewrite that in terms of angles that we do know, and we do know 135 plus 60. So let's think about that before we do anything. Okay. 90 plus 45 is 135. So this is negative square roots of 2 over 2 and positive square roots of 2 over 2. Okay. And 60 degrees is up here, and that's 1/2 comma square roots of 3 over 2. Okay. So these are our two angles. So we know then that the tangent of 135 degrees is equal to the sine, which is square roots of 2 over the cosine, which is negative square roots of 2 over 2, which will reduce to -1. And now we can also find the tangent of 60 degrees. Okay. So that's the sine, square roots of 3 over 2 over the cosine, which is 1/2, which reduces to just square roots of 3. Okay, now that we've done that, this will save us some work in our formula. So we know then that the tangent of alpha plus beta has to be the tangent of alpha plus the tangent of beta over 1 and their product. And since I have a plus here, I need a minus there. Okay, so which is what? Well, 135 is alpha, and 60 is beta. Okay, so the tangent of alpha, well, that's 135, so the tangent of 135 is -1. -1. Then plus, we need the tangent of beta. Beta is 60. Here's the tangent of 60. It's square roots of 3 over 2. Or no, just square roots of 3. Okay. Then we divide that by 1 minus their product. -1 is the tangent of alpha, and the tangent of beta is square roots of 3. Okay, so this becomes, up top is fine, 1 minus the square root of 3 over 1. Now negative and negative become positive, square roots of 3. Okay. Now, if there wasn't a radical in the denominator, we'd be done. Okay. But we need to rationalize this denominator. Okay. So let me remind you how we rationalize denominators. Okay. We have two terms here. So what we need to multiply by then is the conjugate. Okay? We'll need to multiply by 1 minus the square root of 3. And I dropped a negative up here. I have to put that back in. Okay. This is -1. Okay. Good grief, this is -1 plus square roots of 3. And this is 1 plus. Okay, sorry about that, you guys. Okay. Now let's start. Alright, so we're going to have to FOIL. So maybe let me write them down here. -1 plus square roots of 3 times 1 minus square root of 3 over 1 plus square root of 3, 1 minus square root of 3. Okay, so just rewriting this. Alright, now through FOILing. 1 and -1 are -1. Then plus square roots of 3, plus another square roots of 3, and then our last is minus the square root of 3 squared, okay, over 1 minus square roots of 3 plus square roots of 3, then minus square roots of 3 squared, by FOILing. Okay. So up top what we'll have then is negative 1 plus 2 square roots of 3 minus, well, the square root of 3 squared is just 3 over 1, now minus square root of 3 plus square root of 3 will go to 0, which is exactly why we multiplied by the conjugate, and then minus, again, 3. And now we're almost done. Negative 1 minus 3 is minus 4, plus 2 square roots of 3, and down below 1 minus 3 is minus 2. So let's simplify this. This is negative 4 divided by negative 2 plus 2 roots of 3 divided by negative 2. Now here, negative 2 goes into negative 4 a positive 2 times. And here we have to be a little bit more careful. 2 goes into 2 one time, but the negative and the positive become minus. And then we'll carry the square root of 3. So this, as an exact value, is the tangent of 195 degrees. Let's do another one. Let's say we need to find the tangent of negative pi over 12. Okay. So again, we're going to have to find two angles. So the first thing I do is, since it's the common denominator of 12, I know that's what I'm looking for. Okay. And since it's negative, I'm sure this is going to be a subtraction. Well, what would I need for that to happen? Well, 3 pi over 12 minus 4 pi over 12 would be negative pi over 12. And now I can reduce these. 3 goes into itself 1 time and into 12 4 times. This is a known angle. And 4 goes into itself 1 time and into 12 3 times. Now let's find out what these tangents are to begin with. Well, the tangent of pi over 4 is easy. That's just root 2 over 2 over root 2 over 2. So that's just equal to 1. Now pi over 3 is up here. That's at 1/2 square roots of 3 over 2. And we just did that in the last one, did we not? So anyway, sine is square roots of 3 over 2 divided by 1/2. So the tangent of pi over 3 is just square roots of 3. Okay. So now we know our formula. We'll have to take the tangent of alpha, the tangent of beta, over 1 in their product, and then we just have to ask ourselves, well, which is it? Is the plus or the minus that goes here? Okay. So the way I remember it is that tangent is sine over cosine, right? Okay. And remember, these are alphas, plus, or minuses. So when you're in the sine, you use the same sign. And with the cosine, you did the opposite. So with the sine being up top, we use the same sign as what we had here, minus, and this one becomes the plus. Okay. So now we know the tangent of pi over 4 is just 1, then minus the tangent of pi over 3 here is just square roots of 3, and then 1 plus, now the tangent of pi over 4 is 1, and tangent of pi over 3 is square roots of 3. Alright, so this is 1 minus the square root of 3 over 1 plus the square root of 3. And I think that's exactly the one we just did we not? It turns out to be the same. Oh, we had a negative 1 here. Okay, well, we can do it. It never hurts. Let's rationalize the denominator again. Okay, so now to rationalize, we need 1 minus the square root of 3, the conjugate of the denominator, and 1 minus the square root of 3. Okay. Now, by foiling, we get positive 1 minus square roots of 3 minus another square root of 3, now plus square roots of 3 squared over 1 minus square roots of 3 plus square roots of 3. That will go to 0. That's why we're multiplying by the conjugate. And now minus square roots of 3 squared. So this is 1 minus, just combining like terms, 2 square roots of 3 plus 3 over 1 minus, these goes to 0, 3, which is 4 minus 2 square roots of 3 over negative 2, which we can simplify. The negative 2 goes into positive 4 and negative 2 times. Here the 2's will cancel, and negative will become positive. Okay, so it's going to take good bookkeeping skills for us to do this. Okay. We did that one, we've done that one. Alright, let's do the co-function identities. Remember that co-functions of complementary angles are equal. Okay. So how would that look for us? Okay. Co-functions, that's the sine, the cosine, the tangent, the cotangent, the secant, the cosecant. So let's just say we had to look at the sine of pi over 2 minus beta. Alright, co-functions of complementary angles are equal. Okay, so complementary means 90 degrees, and in radians 90 degrees is pi over 2. So what that means is that pi over 2 minus beta plus beta, okay, this angle, plus that would just be equal to pi over 2. Okay. So this angle, pi over 2 minus beta, is complementary with the angle beta. Because if you add them together, you get pi over 2. Okay. So if these two angles are complementary, then what we expect to find is that the sine of this angle is equal to the cosine of beta. Okay. So that's what we suspect, that this should actually be equal. Okay. Because pi over 2 minus beta is complementary with beta. Sine and cosine are cofunctions. Let's see if it's true. Okay. So the sine of pi over 2 minus beta. Let's expand this using the difference formula. So we'll take the sine of the first angle, which is pi over 2. Always the cosine of the second angle, which is beta. I'm in the sine, so we'll take the same SIGN. And then the cofunctions. So this is the cosine, pi over 2, times the sine of beta. Alright. So that was just expanding it. And now let's think about what we know. Okay. Well, we know the sine of pi over 2, right? Here's pi over 2. This is the point 0, 1. So from here, the sine of pi over 2 is just 1 times the cosine of beta, because that's unknown. And then we'll subtract from it the cosine of pi over 2. But the cosine of pi over 2 is 0, so we'll put that in, times the sine of beta. And now it's just algebra. 1 times anything is just itself, so we get the cosine of beta minus 0 times anything is just 0. So it is true that the sine of pi over 2 minus beta is equal to the cosine of just beta. This is because of the cofunctions. Okay. So let's see if we can write these all down. So the sine of pi over 2 minus an angle has to be equal to the cofunction of the angle. Similarly, it would be the cosine of pi over 2 minus beta would also have to be equal to the sine of beta. It'll work both directions because they're cofunctions. The tangent of pi over 2 minus beta has to be equal to the cotangent of just beta. And the other way around as well. The cosine, or the cotangent of pi over 2 minus beta must be equal to the tangent of beta. And the secant of this pi over 2 minus beta has to be equal to its cofunction, which is cosecant, of the complementary angle, which is just beta. And it'll work the other way as well. The cosecant of pi over 2 minus beta has to be equal to the secant of just beta. Okay, so these are the cofunction identities. Now, you can memorize them, or you can memorize the fact that identities, complementary angles, cofunctions of complementary angles are equal. Okay, it's a direct result, or you can work it out using the sum or difference formula. So please get working on understanding all of these different identities. Let's do a few more. With the tangent. Okay, if we have the cotangent of pi over 2 minus pi over 3 plus the tangent of negative pi over 6 over 1 plus the tangent of pi over 3 times the cotangent times the cotangent of pi over 2 minus pi over 6. Well, good grief, if we have to simplify this. What I see up top is a plus. I have a tangent with something. I would really like for it to look like one of our tangent identities here. If I had tangents in the products, okay, ones minus, I could either pick alpha plus beta or minus. The one's already sitting there. I have a tangent. I have a tangent. So the question is, can I make this work? Well, notice here that this is pi over 2 and I'm subtracting some type of angle pi over 3. So this angle, pi over 2 minus pi over 3, that angle, if I added pi over 3 to it, that angle, I'd just get pi over 2. So this angle and this angle are complementary. Okay, so then I know then that the cofunction cotangent is tangent. So this has to be equal to the tangent of pi over 3. All of this, by the cofunction identity. now plus the tangent of negative pi over 6. And divided by 1 plus the tangent of pi over 3. And here again we're in the same situation. Okay. Here I have a pi over 2 subtracting pi over 6. So that angle, pi over 2 minus pi over 6, if I would add pi over 6 with that angle, then I would get pi over 2. So this angle and that angle are complementary. So this, again, is the cotangent, has to be equal to the tangent of the complementary angle, which is just pi over 6. Now we're almost there, looking back. The trouble is I have different signs for both of these. I need a plus and a minus, or a minus and a plus. I also need alphas and betas to be the same. Okay. So now I have a plus and a plus. That's not quite right. These angles are equal. These angles are not. But we can use our even and odd properties and think about this. Well, I'm just recopying pi over 3. Now remember, tangent is an odd function, so this is the same thing as the negative of the positive angle. Okay. And the positive and negative become negative, and then just over 1 plus the tangent of pi over 3 times the tangent of pi over 6. And now I can look back and compare, and this is the formula for minus. Okay. So this has to be equal to the tangent of alpha in this case is pi over 3 minus beta in this case is pi over 6. Okay. But we can simplify that. This is the tangent of, I'd like to have a common denominator since I'm subtracting fractions. Okay. So to do that I need to multiply by 2 and by 2. Okay. And now I can subtract 2 pi over 6 minus pi over 6. Well, this is just the tangent of pi over 6. This is a known angle on our unit circle. Pi over 6 is down here. Square roots of 3 over 2, comma 1/2. So that has to be equal to the sine, which is 1/2, divided by the cosine, which is square roots of 3 over 2, which is the same thing as 1 over the square root of 3. When I simplify it. And then I can rationalize this to get square roots of 3 over 3. And that's how we would simplify this problem. Okay. We could also simplify it to use problems like so. Okay. If, for example, we had to take the sine of the inverse cosine of theta minus the inverse cosine of 1/2. Okay. Well, we have to remember something. If I'm going to take the sine of anything, these had better be angles. Okay. And luckily they are. Remember, this is tell me the angle, let's call it theta. Theta 1, okay, why not? This is tell me the angle whose cosine is 0. This is also represents an angle. We'll call it theta 2. Okay. It says tell me the angle whose cosine is 1/2. Okay. Now we're going to have to worry about the restrictions. Okay. So we're looking for where the cosine is 0. And that happens here in here. Now, which answer is it for the inverse cosine? Well, remember the inverse cosine looks like this with a range. Okay. So the angle that we're talking about here is this one. So that's pi over 2. And we can do the same thing with the inverse cosine of 1/2. The cosine being equal to 1/2 happens here twice. Okay. And again, we decide which one it is by using the restrictions. Okay. So that means we pick this angle, and this angle is pi over 3. So really what we're being asked to do is to find the sine of pi over 2 minus pi over 3. Okay, so let's do that. Okay, this is the sine formula for subtraction, so it's always the sine of the first angle times the cosine of the second angle. Sine, yes, so I'll take the same sine, and then the cosine, the cofunctions, pi over 2 times the sine, pi over 3. It doesn't matter if you put parentheses around it or not. Okay. All right, now let's figure this out. All right, the sine of pi over 2, well, the sine of pi over 2 is just 1. Then we multiply that by the cosine of pi over 3, which is 1/2. And then we subtract from that the cosine of pi over 2, which is 0. So we really don't even care what the sine of square roots of pi over 3 is, but it's square roots of 3 over 2. So this is just equal 1 times 1/2 minus 0, which is just 1/2. Okay, the last thing you're going to be asked to do in this section is to also start working with some more, or keep working with more identities. So let's verify this. Let's say the cosecant of v minus t. Okay, we're going to be asked to show that that is the same thing as the sine of v, cosine of t, plus the cosine of v, sine of t, divided by sine squareds of v minus sine squareds of t. Okay, so remember when we're working with identities, okay, and we're going to be asked to prove this, we can do it in a couple of ways. We can either pick the left-hand side and then work towards the right, or take the right and work towards the left. Okay? We don't work both sides at the same time. So I'm debating which place we should start with here. I do know that this is a sine of the first, cosine of the second, plus. So this is the sine of v plus t. And I'm not quite sure what I would do with this. I might change one to like, this is 1 minus cosine squared of v. I'm not sure how helpful that will be to us. So I might decide to work with this left-hand side because this is the cosecant. Let's start there. Okay. So the cosecant of v minus t, well, we know that has to be equal to 1 over the sine of v minus t. Okay. That's true. Now the only thing I can do is expand this, so this has to be 1 over the sine of v, always the cosine of the second one. It's the sine, yes, so I'll take the same sign. And then the cofunctions. Well, there's not much to do here. So what I'm tempted to do, I'm going to just rewrite this. There's not much I can do, but I could multiply by the conjugate. Okay, so I'd multiply this, the conjugate of this. I'll keep the first one's the same, the sine of b, cosine of t, now plus the cosine of b sine of t. Okay. But I would have to do that on top and bottom. Sine of b cosine of t plus the cosine of v sine of t. Okay. And that's going to be really good because when I multiply 1 times that, I'm going to get this. Okay, so we're on the right path. Okay. So this becomes sine of v cosine of t plus cosine of b sine of t. Alright, so this first one is going to be squared. So we'll get sine of v cosine of t squared. Okay. Now this is going to be the positive, and this is going to be the negative, which is why we multiply by the conjugate. So those two will go away, and I'll just be left with the last, which is minus this cosine of b sine of t squared. Now I want to get to this denominator being sine squared v minus sine squared t. So I think what I'm tempted to do is just distribute or apply this power through. So keeping the numerator the same, sine of v cosine t plus cosine v sine of t over, this would become sine squared v cosine squared t minus cosine squared v sine squared t. From the fact that if you take a times b and square it, that's the same thing as a squared times b squared. Okay, well, I want to get to just a sine squared of v minus the sine squared of t. So I want just these two. All right. Well, then, if we don't have any sines in what we're going for, or any cosines, we have no cosines in here. Let's replace these. Okay. So keeping the numerator the same, sine of v cosine of t plus cosine of v sine of t, just copying. Then sine squared of b. Now, cosine squared of t is the same thing as 1 minus sine squared of t. Then minus from the formula. This cosine squared here, we can turn into 1 minus sine squared of v. Okay. Alright. We're going to get there. Alright, the numerator stays the same. Sine of v, cosine of t, plus cosine of v, sine of t. Now we're going to have to distribute this through and see what happens. So we'll get sine squared v minus sine squared v sine squared t. Okay, these are different angles, so it's not sine to the fourth. And here we're going to be careful, okay? We've got to distribute this sine squared and the negative to both. Okay, so we'll do it at the same time. Okay, so this becomes minus positive 1 sine squared. So that's minus sine squared of t. Now the minus and the minus will become positive, and then we multiply these two. Sine squared v sine squared t. Okay. So you guys are going to need to remember to keep writing your angles down, otherwise you're going to get yourself lost. Okay. But in the end, that does it for us, because now we have like terms. This is minus sine squared v sine squared t, and this is plus, so these will go to 0. And we are left then with just sine of v, cosine of t, plus cosine of v, sine of t, over sine squared v minus sine squared t. And this is equal to the right-hand side, which is what we wanted. Okay, so this should get you through your homework. You'll need to know your identities. So finish your homework and get that put on a flashcard so you can keep working with them, and keep working on how to do these identities and the different techniques that you will use. If you have a question, send me an email.